Lesson 1: Angles in Standard Position. An angle is formed by two rays with a common endpoint. In this illustration, we can see that point B is our vertex or our common endpoint, and the two rays are ray BC and ray BA. Ray BC is our rotated ray or our terminal side, while ray BA is our fixed ray or our initial side. An angle is said to be in standard position if and only if the vertex is at the origin, the initial side lies in the positive x-axis, and if the angle is in the rectangular coordinate system or the Cartesian plane. The angle is said to be positive if it is counterclockwise, and negative if it is clockwise. Measuring angles in radians. To convert degrees to radians, we have to follow this formula. Theta, or the angle, multiplied by pi over 180 degrees. For example, 30 degrees. To convert 30 degrees into radians, we have to multiply 30 by pi over 180. This will be equal to 30 pi over 180, and that will be equivalent to pi over 6 radians. And in order to convert radians to degree, we just have to substitute 180 to pi. In this example, our radian is 2 pi over 5. In order to convert this to degrees, we have to substitute 180 to pi, then proceed. This will be 2 times 180 will be 360 over 5. This will be equivalent to 72 degrees. Quadrantal angle. A quadrantal angle is an angle in which the terminal side coincides with one of the axes in the coordinate system. This means that this is our 90, our 180, our 270, and our 360 degrees. Their terminal sides coincides with either the y or the x-axis. Coterminal angles. Coterminal angles are angles in which the terminal sides coincides with one another. This means that the two angles must have their terminal sides on the same position. In order for this to be possible, the two angles in standard position must differ by an integral multiple of 360 degrees or 2 pi radians. In this example, 30 degrees is coterminal with 390 degrees. This is because their terminal side is at the same position. It is just so that 390 degrees is one full revolution ahead of 30 degrees. In order to find the positive coterminal angle, we need to follow this formula, theta plus 360 degrees. And in order to find the negative, we just have to follow theta minus 360 degrees. Reference angle. The reference angle is the measure of the acute angle in which the terminal side makes with the x-axis. Basically, it is the angle formed from the x-axis up to the terminal side. To compute the measure of the reference angle in every quadrant, we have to follow this. For quadrant 1, it will just be theta, or the angle. For quadrant 2, it will be 180 degrees minus theta. For quadrant 3, it will be theta minus 180 degrees. And for quadrant 4, it will be 360 degrees minus theta. In this example, 70 degrees, our reference angle will also be 70 degrees, since 70 degrees is in quadrant 1. In this example, 120 degrees, our reference angle will be 180 degrees minus 120 degrees, or 60 degrees. This is because 120 degrees is at quadrant 2. For quadrant 3, we have 210 degrees. In order to get the reference angle, we just have to subtract 180 from 210 degrees. This will be equivalent to 30 degrees. Finally, for quadrant 4, we have 345 degrees, for example. In order to get the reference angle, we just have to subtract 345 degrees from 360 degrees. This will be equivalent to 15 degrees. That concludes Lesson 1, Angles in Standard Position. Lesson 2, the circular functions. Let's start with the unit circle. The unit circle is a circle in a Cartesian plane whose radius is 1 and the center at the origin. This circle is described by the equation x squared plus y squared equals 1. Angle in standard position, the sine and cosine functions of the angle are described as y and x. Since the coordinate x and y are unique for an angle in standard position, the equations are actually defined as functions. SOHCAHTOA. It is the abbreviation used to easily identify which side goes with sine, cosine, and tangent. For sine, it is opposite over hypotenuse. For cosine, it is adjacent over hypotenuse. And for tangent, it is opposite over adjacent. This also goes for their corresponding reciprocals. For sine, it is cosecant, which will be hypotenuse over opposite. For cosine, it will be secant, which will be hypotenuse over adjacent. And for tangent, it will be cotangent, which will be adjacent over opposite. The unit circle also contains 4 quadrants. Each quadrant has a different set of signs for x and y values. For quadrant 1, both x and y are positive. For quadrant 2, x will be negative and y will be positive. For quadrant 3, both x and y are negative. And for quadrant 4, x is positive and y is negative. Theta equals 45 degrees. Find the values of the 6 circular functions. Now we can say that if theta is 45 degrees, the other acute angle will also be 45 degrees in order to form a right triangle. This also means that it forms an isosceles right triangle wherein x is equivalent to y. With this in mind, we can use this in the equation y equals x squared plus y squared. and represent y with x, or vice versa, wherein x squared plus x squared, this will be 2x squared, then 2x squared equals 1, which will be x squared equals square root of 1/2. X will be equivalent to square root of 2 over 2. This also goes for y. Now that we have the value of x and y, we can get the 6 circular functions. Since y represents sine, we can say that sine 45 is equal to square root of 2 over 2. This also goes for cosine, since x represents cosine, square root of 2 over 2. And since tangent is y over x, we can say that tangent 45 degrees equals 1. Now, in order to get cosecant, secant, and cotangent, we just need to get the reciprocal of sine, cosine, and tangent, which will be 2 over square root of 2 times square root of 2. This will be 2 square root of 2 over 2, or square root of 2. Same with secant 45, this will be square root of 2. And for cotangent 45, it is also the same, 1. Consider this example. Sine theta equals 5 over 13. Find the values of the other circular functions. We can start off by making a right triangle to represent our angle. Now we know that sine is equivalent to opposite over hypotenuse, meaning 5 is our opposite side of the angle and 13 will be our hypotenuse, or our radius. The missing side is the adjacent side. In order to find that, we have to use the equation x squared plus y squared equals r squared, or the Pythagorean theorem for short. X squared will be the missing, y squared is equivalent to 5 squared, and r squared is equivalent to 13 squared. X squared equals 144, then square root of both sides. X is equal to 12. So now that we know the adjacent side, we can easily identify the other circular functions. Cosine is adjacent over hypotenuse, meaning 12 over 13. Tangent is equal to opposite over adjacent, which is equal to 5 over 12. Now, in order to get cosecant, secant, and cotangent, we just need to find the reciprocal of their corresponding circular function. For cosecant, it will be the reciprocal of sine, which will be 13 over 5. For secant, the reciprocal of cosine, which will be 13 over 12. And for cotangent, the reciprocal of tangent, which will be 12 over 5. Next is tangent theta equals negative 7 over 24, where the angle lies on the second quadrant. Now, this means that the terminal side is in quadrant 2, meaning the triangle must look like this. Now, we know that tangent is equivalent to opposite over adjacent, meaning 7 over 24. But since it is in quadrant 2, remember x is represented as negative and y as positive in quadrant 2. This means that 24 will be represented as a negative. Now the missing is the hypotenuse, or the radius, and in order to find that, again we have to use x squared plus y squared equals r squared. X squared will be negative 24 squared plus 7 squared equals r squared. Solve all that. R will be equivalent to 25. Now that we know the hypotenuse, we can proceed into finding the other circular functions. Let's start with sine. Sine is equivalent to opposite over hypotenuse, or 7 over 25. Opposite over hypotenuse. And cosine is equivalent to adjacent over hypotenuse, which is negative 24 over 25. And again, in order to find cotangent, cosecant, and secant, we just need to get the reciprocal of each corresponding circular function. For cotangent, the reciprocal of tangent, which will be negative 24 over 7. For cosecant, the reciprocal of sine, which will be 25 over 7. And for secant, the reciprocal of cosine, which will be negative 25 over 24. This concludes Lesson 2, the circular functions. Lesson 3, graphs of circular functions. It is stated that the unit circle is a circle whose radius is 1. This means that the x and y coordinates of its x and y axis are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. In radians, it is 0 pi, pi over 2, pi, 3 pi over 2, and 2 pi. In order to graph the function sine, we need to get its y values. First, its x values are from the measure of each radians. And in order to get the y value, we need to get the corresponding range or y of each measure of radians. For 0 pi, it is 0. For pi over 2, it is 1. For pi, it is 0. For 3 pi over 2, it is negative 1. And for 2 pi, 0. Now, in order to graph the Gaussian function, we need to get the domain or the x value of each corresponding measure of radians. For 0 pi, it is 1. For pi over 2, it is 0. For pi, it is negative 1. For 3 pi over 2, it is 0. And for 2 pi, it is 1. If we plot those x and y values, this is what the graphs of sine and cosine will look like. To graph the sine and cosine functions, we need to follow these two equations. This is for sine and this is for cosine. Then we need to find 6 important factors. Number 1 is amplitude. This is the height of the graph. It is the absolute value of A. Number 2 is phase shift. This is the horizontal shift or the starting point of the graph. This is C over B times pi. Next is period. This is basically one full revolution. This is 2 pi over B. Next is endpoint or where the graph will end. This is phase shift plus period. Next is the vertical shift or the vertical displacement of the graph. This is D. And lastly, the interval. This is period divided by 4. It is also important to note that if the value of C is positive, our phase shift would be negative. And if the value of C is negative, our phase shift would be positive. Consider this first example. Y equals sine x. Since it is a sine function, we would use this equation. A equals 1, B equals 1, C equals 0, and D equals 0. Our amplitude is the absolute value of A. This is 1. Our phase shift would be C over B times pi, which would be 0 over 1 times pi, which is 0 pi. Our period would be 2 pi over B. 2 times pi divided by B1 is 2 pi. Our endpoint is phase shift plus period. 0 pi plus 2 pi equals 2 pi. Our vertical shift is the value of D, which is 0. And the interval would be period over 4, which is 2 pi over 4, which is pi over 2. Now it's time to plot the points and graph. First, we need to get the y values of the graph of sine, which is 0, 1, 0, -1, and 0. 0, 1, 0, -1, and 0. Plot all the points, and we would graph y equals sine x. Now it's time to plot the points and graph. First, we need to get the y values for the graph of sine, which is 0, 1, 0, -1, and 0. So, our amplitude is 1, meaning the height of our graph is 1 unit. Our phase shift is 0 pi, meaning we would start at 0 pi. Our period is 2 pi, meaning there should be 1 full revolution by the end of 2 pi. Our endpoint is 2 pi, meaning the graph should end at 2 pi. Our vertical shift is 0, meaning there will be no vertical displacement in the graph. And our interval is pi over 2. Next, plot the points 0, 1, 0, -1, and 0. And there we have it. We have the graph of y equals sine x. Next example is y equals negative cosine x. Since this is cosine, we would follow this equation. A would be 1, B would also be 1, both C and D would be 0. Our amplitude would be absolute value of A, which would be 1. Our phase shift would be C over B times pi, which will be 0 pi. Our period would be 2 pi over B, which would be 2 pi. Our endpoint would be phase shift plus period, which would be 2 pi. Our vertical shift, which would be D, 0. And our interval, which will be period over 4, which is 2 pi over 4, it will be pi over 2. Now, it's time to graph and plot the points. But first, we need to get the y values of cosine graph, which would be 1, 0, -1, 0, and 1. But of course, we won't just graph it, because as we can see, it is negative. And because it is negative, we have to mirror the graph, or we have to start from the negative. So this will be -1, 0, 1, 0, and -1. So -1, 0, 1, 0, and -1. Plot all the points, and you would have this graph. This is now the graph of negative cosine x. Consider this last example. Y equals 2 sine quantity x minus pi over 2 plus 3. Since this is a sine function, we would follow this equation. So A would be 2, B would be 1, C would be 1/2, and D would be 3. For our amplitude, it will be absolute value of A, which would be 2, our phase shift, which will be pi over 2, our period, which will be 2 pi, and our endpoint, add both of this, which will be 5 pi over 2. Our vertical shift would be 3, and our interval would be pi over 2. Now it's time to plot the points and graph. Since our amplitude is 2, this means the height of our graph would be 2 units. Our vertical shift is 3, that means there would be 3 units of vertical displacement in our graph. Our phase shift is pi over 2, that means our graph would start here, and it would end in 5 pi over 2, which would be here. Now we have to get the y values for the graph of sine, which would be 0, 1, 0, -1, and 0. But we have a vertical shift of 3. This means 3 would basically be our 0 line. So 0, 1, 0, -1, and 0. Plot all those points, and we would have the graph of y equals 2 sine quantity x minus pi over 2 plus 3. That concludes Lesson 3, Graphs of Circular Functions. Lesson 4, Trigonometric Identities. Trigonometric identities are equations involving the trigonometric functions that are true for every value of the variables involved. Some of the most commonly used trigonometric identities are derived from the Pythagorean theorem, like the following: sine squared theta plus cosine squared theta equals 1, tangent squared theta plus 1 equals secant squared theta, and cotangent squared theta plus 1 equals cosecant squared theta. There are also the reciprocal identities, such as sine theta equals 1 over cosecant theta, cosine theta equals 1 over secant theta, tangent theta equals 1 over cotangent theta, cosecant theta equals 1 over sine theta, secant theta equals 1 over cosine theta, and cotangent theta equals 1 over tangent theta. Lastly, we have ratio or quotient identities. This is tangent theta equals sine theta over cosine theta, and cotangent theta equals cosine theta over sine theta. These three identities, the Pythagorean, reciprocal, and ratio, are known as the basic identities. Simplifying trigonometric identities. Consider this example: secant theta times cosine theta. We need to make it so that our answer would only result in one term. And in order for us to do that, we need to find the specific trigonometric identity. In this case, we will change secant to 1 over cosine theta, which is its reciprocal identity. Now we can proceed to multiplication. This will be cosine theta over cosine theta equals 1. Next example is 1 plus tangent squared theta. With this, we can use the trigonometric identity derived from the Pythagorean theorem, which is tangent squared theta plus 1 equals secant squared theta. These two can be interchanged, which means that our final answer is secant squared theta. Example number 3, cosine theta times tangent theta. With this, we could use the ratio or quotient identity. Copy cosine theta and change tangent theta to sine theta over cosine theta. Cancel, and our simplified answer would be sine theta. Proving trigonometric identities. Consider this example. 1 plus cosine x over sine x equals cosecant x plus cotangent x. In proving trigonometric identities, we could either choose to use the left-hand side or the right-hand side to prove. In this example, I would use the right-hand side. We can start off by changing cosecant x with its reciprocal identity, which is 1 over sine x, plus cotangent x with its ratio or quotient identity, which is cosine x over sine x. Since both of them have the same denominator, we can proceed to addition. So our answer would be 1 plus cosine x over sine x, which is equal with our left-hand side. This means we just proved that 1 plus cosine x over sine x is indeed equal to cosecant x plus cotangent x. That concludes Lesson 4, Trigonometric Identities. Lesson 5, Other Identities. First, we have sum and difference. These are basically the expanded forms of this. For cosine, it is easier to remember as cos, cos, sin, sin. And for sine, sin, cos, cosine. If for cosine the sign is positive, you would just change it to negative. And for sine, the sign would just be the same. Next, we have cofunction. The identities are as follows. Sine theta equals cosine 90 degrees minus theta. Cosine theta equals sine 90 degrees minus theta. Cotangent theta equals tangent 90 degrees minus theta. And tangent theta, we have cotangent 90 degrees minus theta. For secant, we have cosecant 90 degrees minus theta. And for cosecant, we have secant 90 degrees minus theta. Equivalent cofunction. Consider this example. Sine 30 degrees. Its cofunction would be cosine 90 degrees minus theta. This will be cosine 90 minus 30, or cosine 60 degrees. Sine 30 degrees equals cosine 60 degrees. If we input this in our calculators, we would know that sine 30 degrees is equal to 1/2, and cosine 60 degrees is also equal to 1/2. This means that sine 30 degrees is indeed equivalent to cosine 60 degrees. Simplifying. In this example, sine 8x cosine 3x minus cosine 8x sine 3x, we could simplify this by looking for the trigonometric identity that has the same pattern. In this case, it is sine alpha minus beta. This is because the pattern is sin, cos, cosine, meaning it has to be sine. Next is we need to identify the alpha and the beta. The first variable will be the alpha and the second will be the beta. This means sine 8x minus 3x. Simplify, it will be sine 5x. This will be our final answer. Finding the exact value using the sum and difference. Consider this example. Given sine alpha equals 5 over 13 at quadrant 1 and tangent beta equals negative 7 over 24 at quadrant 2, find the exact value of sine alpha plus beta. First, we need to get the 6 circular functions of both alpha and beta. In this specific example, I would be using the example I used in lesson 2. So, sine alpha equals 5 over 13. Our missing side would be our adjacent side, which is equal to 12. This means that our cosine alpha would be 12 over 13. Our tangent alpha would be 5 over 12. Our cosecant alpha would be 13 over 5. Our secant alpha would be 13 over 12. And our cotangent alpha would be 12 over 5. Next is for beta. We have tangent beta equals negative 7 over 24. Our missing side is our hypotenuse or our radius, which is equal to 25 using the Pythagorean theorem. Sine beta would be 7 over 25. Cosine beta would be negative 24 over 25. Cosecant beta would be 25 over 7. Secant beta would be negative 25 over 24. And finally, cotangent beta would be negative 24 over 7. Once we have the 6 circular functions of alpha and beta, we can now find the exact value of sine alpha plus beta. If we expand that, it will be sine alpha cosine beta plus cosine alpha times sine beta. We just have to look for the circular functions here. Sine alpha would be 5 over 13 multiplied by cosine beta would be negative 24 over 25 plus cosine alpha would be 12 over 13 times sine beta, which would be 7 over 25. Solve all that, we will have the final answer of negative 36 over 325. This is the exact value of sine alpha plus beta. That concludes Lesson 5, Other Identities.